Hi everyone, welcome to our first activity of the seminar that we are holding after 2 years of pandemic. As you know, we haven't done any face-to-face activity or seminar last 2 years, so this is very exciting seeing all you here. And I would like to thank you all, and also Osman Barış MALCIOДLU, who is an academic fellow of Physics department. Introduce you now and give the stage to you. Okay. Thank you again.
So I hope you are able to hear me very well. Well, yeah, it's a technical issue. The moment, please. Yeah, I lost the connection. What a pity. Okay, now we are back. I usually give my lectures in this class and nothing was happening up until today, only minor technical issues, but well, there is first for everything. So first of all, I mean, scientific point of view, what am I interested in? I'm really interested in these two topics, the transition between the quantum realm and the classical realm. I mean, this is something that has always been very intriguing to me, and I try to approach this problem using condensed matter physics. You know, for example, if you are dealing with high energy physics, you can ask this question, what is elementary particles? And one more interesting question is that if it is elementary, how does it decay and why does it decay? So this has a corresponding question like excitons in condensed matter physics, and I find it for myself more tractable. And if you want to understand me, why I am interested in this topic so much, please go and check this famous paper by Anderson. So Anderson wrote this paper when a famous physicist at that time said that, yeah, we solved everything, you know, physics is just applied mathematics, and since chemistry is applied physics and biology is applied chemistry, then we don't need to do science anymore. Anderson was very angry with this comment, and he wrote this paper, why biology is not chemistry, and chemistry is not physics, and physics is not mathematics. So this is something I really suggest everyone to read. Okay, now nowadays I'm really interested in quantum computers, and when you ask why quantum computers are interesting for a physicist or a basic scientist, it goes back to this famous quote of Feynman. You know, nature works with quantum principles, and it's a very complex problem, and it's very much fun, so you can read this. And at the moment, I mean, I don't know if you ever wondered how was it to be living in this moonshot race, moon race. Everyone was trying to land on the moon. There were these technological advancements every day, and there was this inventions, and there was this excitement. Yes, at the moment we are living in such a moon shot time, and there are several reasons for this. Economy is one of the problems, and a lot of countries are investing heavily on quantum computers. This is one of the next moonshot projects, and everyone is, let's say, trying to be the first to reach this goal. Europe has a very well-defined moonshot problem, so we are at the moment around here. So they already have the metrology, so they already almost established the infrastructure. Now they are trying to build this computing and simulation infrastructure, and thanks to this huge amount of money and interest and all these clever people rushing into the field, quantum computers are already here. So they arrived 50 years before we were expecting them. We have usable quantum computers now, but the problem is that only very few people can use it. So what is missing in this moonshot project are the, like say, astronauts, the people that are capable of using quantum computers. So that is why I started working on this, not only because it is a very, very useful tool for a scientist, because, you know, basic science, everything is working with quantum, and what is the better tool than a quantum computer to understand how things work. But also since this is kind of an interesting concept. By the way, just a little bit of interleave. I mean, I am old. When I was little, when I was going to the primary school, a computer, I mean, this was before the cell phones, not even smartphones. We didn't have cell phones much later in my youth. So we didn't have computers. Computer was a very, very exotic thing. Some people were buying computers as toys because no one knew a better use for a computer other than toys. At that time, Ankara was a very different place as well. My primary school was in Akay, and I was going by walking to college, which my house was, and everywhere was green, and most of the university students under these trees, they were these were huge pedestrian roads. They were trying to raise some awareness about the computer technology. So they were preparing these photocopied magazines, and they were teaching us little children how to program them, how to do things beyond the games. Then now we cannot imagine a life without a computer. So this was the first transition I have witnessed in my life. The second transition was the internet. So before, I mean, internet became, let's say, accessible when I was going to the middle school. TÜBİTAK had this laboratory open to the public, like a library, which you can go and connect to the world. You were able to communicate with the world. And I remember vividly that I was around, I don't know, maybe 12 years old. I bribed the security guard so that I can stay past midnight. So I was communicating with some people. So I was kind of curious how it will go. And now we cannot imagine a life without an internet, and these quantum computers are making me as excited as these two things. So maybe, I don't know if I will be correct or not, but I think this will be something that will transition our lives. So the thing you have seen here is what we call a qubit. This is the most simplest let's say, element which you can construct a quantum computer on. It's a superposition of two states. So when I call a superposition, it's not either 0 or 1. It's not a mixture of 0 and 1. It is simultaneously all the states between 0 and 1. And we can do computation with it. We can write programs with it, and these programs can be written in some different methods. This a circuit diagram. You music score. So you read it from all these individual elements are the qubits. So this is a qubit line. And these squares you see over there are operators. So these operators, which are represented with some letters in boxes, act on a single qubit, but you will notice that some of them act on both qubits. So these are multi-qubit operations, and these are the readouts, because, you know, in quantum mechanics, when you read something, you collapse the wave function, then you go to the classical realm. So what is this circuit? This is the Stern-Gerlach experiment. As a physicist, this is a, let's say, initiation ceremony. So most of the quantum books start with the Stern-Gerlach experiment. It's an introduction to how strange and far away from our daily experiences the quantum world is. It is about the description of a superposition, which is not a mixture. It's a superposition of all these states, and you are expected to understand this via your imagination, because that experiment used to be inaccessible for most of the students, especially in countries like ours, where these experiments can be quite costly. But now, with this quantum computers, for free, you can sit in front of your computer, just draw a diagram, and you can do this experiment. And by doing this experiment, you understand things that are beyond your imagination. You know, you understand the tricky parts of the experiment. What are the things they are trying to communicate to you? So this is, I find this super interesting. Not everyone finds it super interesting, but I find it very, let's say, motivating. Another thing that is super confusing for people who are not initiated in quantum, let's say, the tools of quantum mechanics. I mean, this is from XKCD. This is one of my favorite comics in the internet. It is about, you know, how philosophical questions are and how much mathematics you need to understand them. Since quantum has some very deep philosophical questions, and most of the people don't have enough mathematics to understand the answers, people really make some very strange claims about quantum mechanics. So I don't know, most of them are very wrong. So this is a very famous example. This is the delayed choice quantum eraser. Does anyone here know of this delayed choice quantum eraser experiment? It's very famous. It's the double slit experiment. I'm sure you all know the double slit experiment. You know the strange world of double slit experiment. When you observe and you put a detector in this screen, they behave like particles. When you remove the detector, they behave like waves. So this is wave-particle duality. So this is one step further. So what you do is that by using this splitting crystal, you create these entangled photons, and after a while you can make this fiber as long as you want. You do the measurement after the first photons, the first pair of photons reach the screen. So these guys, where you are doing the measurements, can be very farther away. So it means that these measurements will happen, classically thinking, later than the observation here. And what you have here is that you have the same type of splitting mirror, which can either detect where this slit is coming from, or you can, let's say, combine these two beams, and you can design a detector that will measure the wave-light picture. So whenever you are measuring things from the wave-light detector, you see a wave pattern. And whenever you are detecting things from the particle light detector, you see a particle light pattern. But the interesting thing is that this is happening after these photons reach the screen. So am I going back in time? So classically thinking, if you are kind of, you know, in this classical mentality, this is equivalent to, let's say, going back in time, but of course not. You are not breaking the rules of relativity. So the trick is here, the coincidence counter. And when you are doing this algorithm with the quantum computer, you understand why this guy that is usually omitted when people are doing some popular things about the delayed choice quantum eraser. They really omit this very important aspect. You really understand why it is not traveling in time. So this is, I suggest you to go and check this out and see. Okay, for those of you who are not very much motivated by these basic science concepts, why these countries are investing so much money, why this became a moonshot project is, let's say, one of the biggest selling points is the Shor's algorithm. So Shor is this guy, very nice mathematician, very interesting personality, very pleasant to listen to. And he devised an algorithm that is, let's say, a threat to the internet security. So whenever you are doing a transaction, whenever you are using your credit card, or whenever you are doing online banking, you are encrypting your data with an algorithm that is not reversible. not reversible in the practical sense, in the sense that this algorithm will, with a brute force attack, will take something like 300 trillion years in order to crack. But Shor's algorithm with a quantum computer demonstrates that this can be cracked in 8 hours. So this is a huge threat to internet security. I mean, 8 hours is nothing. Imagine that I can read all your messages, access to all your bank accounts or whatever. So this can scale up. You know, the Snowden crisis, Chinese were especially worried about Americans listening to their communication. So they started investing heavily on quantum encryption and quantum coding. So this became a selling point. And another big announcement was the Google's Supremacy announcement. Maybe you remember this from a couple of years ago. Google said that, okay, I declare quantum supremacy. Yeah, I am the winner. So what does this mean? Did they just won over all the world? Do they have all your data? Yes, they do have all your data, but not with this quantum computer. This is something completely different. This is the quantum computer they did. This is the typical chandelier formation. So what you have here is these electronic readout circuits and a cryostat, which takes this chip, which is situated on the bottom, to very, very low temperatures, and then it reads out the correlated things. So what they did is that they devised an algorithm that is particularly good for their quantum CPU, but it is extremely difficult for other classical computers. So a classical computer would require around here to solve this problem. So this was their algorithm, but their quantum computer solved them in no time. So this was like the supremacy. This was a proof that they were doing something better than a classical computer. That was very specific, and it didn't have any practical use. It was just for demonstration. So what do we need in order to have a practical application where we don't have any more internet security? We need around 2,000 physical qubits, which amounts to around 200 logical qubits. And a couple of days ago, IBM already announced a Eagle processor which has 127 logical qubits. So people were expecting this to happen in 2050, and we have it today. So this is how fast things are going. So there's a huge talent loss. The hardware is already here, but there are not many people who are using it effectively. And by 2023, they are expecting something like 1,000 qubits with these kind of devices. And when you have 1,000 qubits, then you have pretty much qubits to do error correction and whatever. Then we will be living in a different world. So, okay, so this was what I was saying. We are at the moment, today, what we call near medium scale noisy, intermediate scale noisy quantum computers era. So they are noisy in the sense that the bit flips errors are 1 trillion times more likely to happen than a classical computer. So this is a very big issue. But you have a moderate number of qubits to play with, and this is something that was, broad quantum advantage was expected in 2050s and more. This is happening probably in 2 or 3 years' time with if IBM is able to continue what they claim to do. And as you can see, the market share and people investing in this technology will increase accordingly. So this is the expected projection. At the moment, of course, I mean, this is very small, but people are probably more interested in quantum sensing and cryptography, and quantum computation is very small, but as the time progresses, people are expecting quantum computation to be the dominant use of a quantum device. quantum sensing is extremely important. I don't know if you know squids or gravimeters. Quantum gravimeters are already a thing. They are commercial. So a gravimeter is a device that measures the gravitational anomalies. Like on Earth, we are not in a homogeneous environment. If you have a lack of density, like a gas pocket, then this registers as a change in gravity, and you can detect whether you have oil reserve or gas reserve. And with this quantum gravimeters, which is a commercial product now, you can do it on using satellites. So you don't even need to be on a ship, or you don't need to be on the ground. You can do it from a satellite because they are that, let's say, sensitive. So this is already happening. This is already an established technology, and cryptography is already, the Chinese demonstrated quantum communications, entangled photons with a satellite. So probably they have these kind of things as well. So Europe really doesn't want to stay behind. So they suspect that United States or China has something, and they are not telling. Why are they paranoid? Because this happened before. I don't know if you know the story of the Colossus computer. So the first computer, Colossus, was in 1940s, but it was being used for military purposes, for decrypting communications of the Germans. So it was not announced for 30 years. So it was kept a secret for 30 years. So Europe doesn't want to stay behind, and they also don't want to let's say, this was rather recent. I think it was in 1970s or 60s. Europe was embargoed by United States for computer parts because they were selling computer parts to Bulgaria, and they don't want to rely on United States technology alone. They don't want to be embargoed from a critical technology, this moonshot technology. So they have a very strict quantum technology readiness level scala, which they are promoting a lot. So if you ask me what am I doing on the scala, I am concentrating on QTRL2, which are quantum algorithms. But in this department, there are a few of your teachers that are on QTRL3, so they are doing qubits, they are manufacturing qubits, they are doing even more than 1 qubit. And then in Turkey, you can see some other levels of technology, quantum technology readiness levels as well. So I'm not an experimentalist, I'm a theorist, but like the Velcro band, you know the Velcro, the jirt band, is a consequence of this moonshots program. So it was invented for the astronauts. Now we use it daily in our lives. There are a number of things, technological challenges we have to solve in order to make this quantum computers reality. They are indicated by these reds, you know, these cooling technologies, energy readout technologies, electronics and whatever. And they are actually quite difficult, because what you want to do is that you want to maintain a quantum state for a very long time so that you can do computation, but at the same time you want to immediately read it, and you want to control it immediately without any hassle. So these are competing, because if in order to make this long-lived, you have to make it isolated. If you make it isolated, you cannot control it, or you cannot read it. So solving these challenges are already giving us a lot of patents, a lot of interesting ideas, and let's say applications that are beyond what this project is about. And if you are from physics and astronomy, you are very lucky, because most of these things are coming from physics and astronomy. The engineering people, they didn't catch up with the number of patent applications and number of, let's say, solutions for these problems yet. And well, yeah, okay. So there are a number of ways in order to construct these machines. The IBM's technology is about superconducting circuits. So this is the American ones. They are really backing this up. So these trapped ions and spins and neutral atoms, Europe is investing on them. I don't know what happened to the rest of them, but with the spin and the silicon devices, there has been really significant developments. They did this silicon chips. And photonics, China is very good with photonics systems, also Netherlands. Also here in our university, we have Emre Yüce Hoca that is working on these photonics aspects. Also Alpan Bek Hoca, you can go and talk with them if you are interested in this experimental side of things. So this is, let's say, the development I was talking about. So you can use the technology of the silicon systems in order to harness the power of quantum computers. This is a graphene-based bolometer in order to detect the energy levels of a quantum qubit system. We are harnessing these very exotic properties. So this is also leading to some understanding of beyond single particle levels in two-dimensional systems. So I mean, if you have been to an electronics lesson, a silicon lesson, most of the things you treat them as single particles. You treat each electron as an individual particle. But if you confine these electrons into a single level, which is called a flat band, in graphene you have this Dirac cone, they start interacting strongly with each other, and the single particle picture breaks down. You have these exotic effects like topological states, Weyl fermions, and whatever. And understanding this enables you to do these kind of devices, and it is also helping us understand some of the effects we see in high energy particle physics, for example. So this is, let's say, having conclusions that are beyond the technological achievements, let's say. So this is, I don't know, 2020, Netherlands announced that they have constructed a quantum network between two cities. So they are using telecom fibers, nothing fancy, and they are sending entangled photons to cities, kilometers away. So this is a very significant achievement as well, and this is one of my friends is working on this. So in order to understand the financial systems, it's a very complicated problem. You can use techniques that you already know in quantum mechanics, but they are very difficult problems as well. So you can just, let's say, use Ising models or the Hubbard Hamiltonians, which are more tractable in quantum computers. You can do approximations beyond things. So what can you do? So okay, this is a little bit of advertisement on Q3RL2, what I am doing. There are a lot of, I mean, these companies are looking for talent. They provide free training. You can apply for their scholarships. You can go abroad and they will teach you. But they also provide development kits, and they are online. I am at the moment using IBM's Q service. It's an online free service. It has even more capabilities if you are a teacher and if you are enrolled in a class. So you can start using it for free, but there are also other alternatives that you can initiate yourself with quantum programming. And this is already being used for very big scale commercial intractable NP-hard problems, like solving the air traffic in Europe. So this is the Jülich computer. So they are using simulators, quantum simulators, not actual quantum computers, but quantum simulators, in order to solve this problem, which is really, really hard to solve otherwise. So at least on algorithm-wise, we are already observing some benefits. And quantum cryptography, if you want to land a job, this is the way to go, especially in Turkey. People are very much interested in quantum cryptography. There are some references if you want. And if you want to become a well-paid developer in NISQ era, noisy intermediate scale quantum computer era, this is one of the technologies that you have to invest on. This is called quantum machine learning. The quantum machine learning has some advantages. So these are some various ways of doing, let's say, machine learning algorithms. The first advantage is that you can be noise tolerant. And second of all is that in a classical machine learning artificial intelligence problem, more data does not mean that you will have a solution. There is this entropy limitation, and even if you put more high quality data to a particular neural network, if it's beyond its expression capability, that neural network will not learn anymore. But quantum computers, since you have this entanglement, I mean, if you want to do what is called a quantum advantage, you have to take advantage of quantum effects, and entanglement is the most important one. You can create the increase the expressibility of quantum neural networks. So this is something like a very, very hot topic, and this differentiable quantum circuit algorithms are mostly for Hamiltonian simulations and variational quantum algorithms. A variational quantum algorithm is an algorithm that utilizes the strong points of a traditional computer combined with the strong points of a quantum computer. So they want to cancel the weak points of each other. And this is a hot topic. In order to be able to do that, you have to have a very good, let's say, differentiable, rotatable unitary operator. It's a very difficult problem. And before I finish, I promise this is the last slide, just an advice. Since there is this much of money, it's a moonshot project, there are many, many places that you can benefit. You can, let's say, take the low-hanging fruits from this initiative. Two important ones are this Munich Quantum Valley. So Munich Quantum Valley is not just providing training, but it is also providing you with jobs in industry and also in academia. I mean, practically every university, big university in the world, either started quantum graduate programs, quantum computing graduate programs, or they have institutes that are completely devoted to it, and they organize in these kind of things. In Europe they like organizing, so you can go and apply for there. And the second one is the QSoft. These are Europe specific, but if you are interested in IBM is providing scholarships, and they provide, I mean, Q Turkey. You have to really go and visit Q Turkey. They are doing an exceptional job introducing these technologies to the community. I find them equivalent to these guys sending these, I don't know, they helped me a lot, these university students. When I was going to the primary school, I told you, they were trying to educate us with these photocopied newspapers. They were teaching us how to do programming. I think they are doing the same, so I want to support them as much as possible. They are doing exceptional job. Go and visit their website, and they provide training, Q Bronze, Q Silver. Take these certificates. I think that will be quite useful for you. So this is my web page. I also offer one of the many quantum computing courses in this university. Is a course that is offered by me, but I really recommend you to take the course of the quantum information theory before taking my course. Mine is more application oriented. And if you want to see even more resources and job announcements, there are some job announcement lists that I mentioned in this website page. You can just go and check this. So before I finish, I just want to show you where my projects are. So this is the situation with my projects at the moment. Okay then, so do you have any questions? Nothing? Okay then. Tabii. Hayır. Ben. Ben solid state konularını kullanarak şey yapıyorum, bu konuya yaklaşmaya çalışıyorum. Ama işte Photonic Society, özellikle bizim üniversitemizde fotonik konusunda, tabii o da solid state gibi bazen insanlar düşünebiliyor ama tamamen farklı bir dal. Fotonik üzerine çalışılıyor genelde bizim şeyde. Solid state bu işin ilgisi, bir söylediğim gibi işte bu silikon device'lar. İkincisi de bu readout device'lar, işte bu bolometer, grafin bolometer kısımları falan. O oralarda işin içine giriyor. Yani mesela NV vacancy, nitrogen vacancy defect hiç duydunuz mu? Normal işte şeyin içinde, diamond'ın içinde, elmasın içinde bir tane nitrojen koyarsanız orada bir tane spin defect oluşturursunuz ve bu spin defect çok rahat bir şekilde kontrol edilebilir bir şey. Bu o kadar rahat kontrol edilebiliyor ki ben Almanya'da çalışırken bunun üzerine çalışan bir profesör buluşunu sattı. Nereye sattı? Hani orduya mı sattı, işte şeylere mi, karanlık şeylere mi sattı? Hayır, Bosch'a sattı. Bosch bunu niçin kullanıyor? Hani egzotik kübit bilmem nesi niçin kullanır Bosch? Bu duvarda hani bir delik açacaksınız matkapla. Bu işte elektrik borusunu rahatça bulabiliyorsunuz. Bir kalınlık hani şey varsa, kiriş varsa onu da rahatça bulabiliyorsunuz. Bu detektörler var. Ama su boruları çok büyük problem. Çünkü su boruları o detektörler tarafından, hani plastiğin içinden de, yalıtımlı şeyin içinden de geçiyor. O su borularını bulmak çok zor. Ama buradaki Diamond NV vacancy'leri kullanarak suyun işte polarizasyonunu çok rahat bir şekilde görebiliyorsunuz. Su dedektörü olarak kullanılıyor. Yani hani bu cırt cırt bant teknolojisi, hani kübit yapıyorsunuz ama su detektörü olarak kullanılıyor. Öyle cırt cırt bant teknolojilerine bir örnek daha. Solid state böyle şeylerde buraya giriyor. Konuya giriyor. Başka? Tabii. Quantum Information, Sadi hocanızın. Evet. Şimdi şöyle bir şey var. Şimdi Python bildiğinizde Qturkey'e gidebilirsiniz. Çok güzel bir şekilde Q-Bronze'u yapmak için hafif bir kuantum konusunda, işte tensör algebrası konusunda bir bilgi, bir de Python ile onları yapabileceğinizi düşünüyorum. Ama benim bu konuyla ilgili heyecanım Qturkey'in heyecanıyla %100 örtüşmüyor. Çünkü Qturkey biraz daha böyle bilgisayar computation tarafına, biraz daha mühendislik tarafına yakın anlatıyor bu şeyleri. Q-Bronze'u, Q-Silver'ı. Ben ise biraz daha böyle hani işte ne bileyim Stern-Gerlach experiment'ını yapabiliyorsunuz falan gibi temel bilim kısmıyla ilgili heyecan duyuyorum. O küçük nüans farkları ama yani hani bu farklardan da haberiniz olsun. Benim kendi dersim için bu Quantum Information Theory'yi almanız iyi olur derken mesela ben işte ne bileyim Shannon entropisinden bahsediyorum. Ondan sonra işte şeylerden bahsediyorum. Entanglement'tan falan bahsediyorum. Bunu nasıl, mesela bozonik bir wave function kullanarak fermiyonik bir wave function'ı nasıl construct edebiliriz gibisinden soruları göstermeye çalışıyorum. Orada biraz işte Sadi hocanızın dersi olmadan biraz şey olabiliyor, sıkıcı gelebiliyor insanlara. Hı? Tamam. Herkes burada fizikçi mi? Kaç kişi fizikçiyiz? İyi, çoğunluğumuz fizikçi. Peki başka nereden geliyorsunuz? Havacılık, çok güzel. Başka? Matematik, havacılık. Tamamdır. Havacılıkta akışkanlar dinamiği üzerinde bu konuların, özellikle akışkanlar dinamiğinde non-linear Navier-Stokes'ta bunların uygulamaları var. Ben de bu konuda bir proje üzerine çalışıyorum şu anda. Navier-Stokes denklemleri aslında kuantum akışkanlar dinamiğinin özel bir hali. Arasındaki geçiş kısmında çok ilginç şeyler yapabiliyorsunuz autoencoder'larla. Öyle aklınızda bulunsun. Matematik konusunda da bakacaksanız olayı tabii ki özellikle bizim informatikte çok iyi matematikçi hocalarımız bakıyorlar. Çok ilginç bir konu. Quantum resistant cryptography. Yani bir kuantum bilgisayarın çözemeyeceği algoritmalarla kriptografi yapmak ilginizi çekebilir. Bakabilirsiniz. Başka cevaplayabileceğim bir şey var mı? Şeyde var bu dediğim, ondan sonra YouTube'dan durdurup bakabilirsiniz. Onun altına da comment olarak ekleriz. Başka? Tamamdır o zaman. Yani bu benim dediğim gibi nasıl bilgisayarsız işlerimizi yapamaz hale geldik. Temel bilimde de kuantum bilgisayar olmadan işlerimizi yapamaz hale geleceğimizi düşünüyoruz. Çok güzel bir analoji yaptılar Q-Turkey'de. Bu bir tren yavaş yavaş hızlanıyor. Ondan sonra bir noktadan sonra çok hızlı gitmeye başlayacak. Atlamamışsanız geride kalacaksınız. O yüzden daha bu tren yavaşken atlarsanız iyi olur geleceğiniz için. Ondan sonra yani ilgilenmiyorsanız bile konuda bir yerden nasıl bilgisayarla ilgilenmeseniz bile kullanmak zorunda kalıyorsunuz. En azından belirli bir şey yapmaya çalışınız. Tamamdır. Oldu. Çok teşekkür ediyorum burada olduğunuz için. İyi akşamlar o zaman.